Welcome to the third part of the online presentation on how to use MATLAB and Simulink to solve differential equations. This problem is presented in relation to the application of vertical motion of a rigid sphere under the influence of gravity and aerodynamic resistance. In part 3 of the presentation, we will present the testing and validation of the simulation model. As mentioned in part 2, the simulation model was constructed using Simulink, which is a toolbox of MATLAB, and it's presented here in this slide. For the testing of the simulation model, we need to run the simulation for different scenarios and gather the simulation data with an appropriate block from the Simulink library, which exports the simulation data as a time series variable in the MATLAB workspace. Once the data in the MATLAB workspace are then imported into a MATLAB script and analyzed and plotted. The first experiment to be conducted is a free fall experiment from an initial altitude of 300 meters and an initial speed of 0 meters per second. So we have a sphere of 200 grams and diameter 10 centimeters. Initially, we would like to plot the trajectory of the velocity and altitude of the sphere for the two cases. The first case is when we have aerodynamic resistance, which is plotted in color blue. The second case is the simplified case without aerodynamic resistance, which also admits an analytical solution to the differential equation. The two cases are presented here. As mentioned previously, the blue line represents the solution from running the simulation model, while the red line represents the analytical solution since it corresponds to the simplified case without aerodynamic resistance. It's interesting to know that the case without aerodynamic resistance corresponds to an analytical solution for the relationship between the speed and the altitude of the ball, which predicts that the final speed of the ball will be 76.71 meters per second. This is this point here, which corresponds to 0 altitude. So this plot shows the altitude of the ball plotted on the y-axis in meters against the velocity of the ball plotted on the x-axis in meters per second. So the ball starts with 0 velocity at this point here and altitude 300 meters, and as time progresses, the trajectory of the ball is changing until the altitude is reduced to 0, at which point the simulation stops because the ball reaches the ground, and then in this case the ball has a certain velocity. Obviously, for both cases the velocity is negative because the ball is pointing downwards towards the ground, and it's interesting to notice that for the case of aerodynamic resistance, the ball achieves a terminal velocity, meaning the velocity does not increase further up to a certain time. It becomes constant, pointing downwards until the ball reaches the ground at this point here. The terminal velocity is a well-known phenomenon in the case where we have free fall under gravity and aerodynamic resistance. When there is no aerodynamic resistance, it's obvious that the ball velocity continues to increase and there is no terminal velocity in this case. One final comment is to notice that the equation describing the trajectory of the ball as a function between the velocity and the altitude is actually a representation of the conservation of mechanical energy of the ball. This term on the left of the equation is related to the change in kinetic energy, especially if we bring the 2 down at the denominator and multiply by the mass of the ball, and also if we multiply by the mass the right hand side, then this corresponds to the change in potential energy. So the two are equal, which implies that there is conservation of mechanical energy in the case where we don't have aerodynamic resistance. This slide presents in more detail the plots of velocity against time and altitude against time for the previous experiment. It's a more detailed plot in the sense that it presents both the velocity and the altitude as functions of time. And again, the case of aerodynamic resistance is plotted in color blue in both cases, while the case without aerodynamic resistance is plotted in color red. It's interesting to notice again the range at which we have achieved the terminal velocity. In this case, the velocity is constant and negative, and a constant velocity, once it's integrated, produces a linear change in the altitude as expected. It's very interesting to notice that for the case of aerodynamic resistance, the ball takes a longer time to reach the ground, as shown from the altitude plot here. It takes just over 12 seconds, while in the case without aerodynamic resistance, the ball reaches the ground quicker, just under 8 seconds. And the reason being, the aerodynamic resistance decelerates the ball, and therefore it takes longer for the ball to reach the ground. Another important point to notice is that for the case without aerodynamic resistance, the expression of the velocity is linear as expected because it's equal to minus g times the time. Therefore, it's a linear line with slope minus g. And if we remember that g is approximately equal to 10, then this red line has a slope of minus 10, which is correct because every 2 seconds the speed increases by minus 20 meters per second, which is the ratio minus 2 over 2 is minus 10 is the acceleration of gravity. Obviously, in the case of aerodynamic resistance, this slope is becoming smaller and smaller until it becomes 0, simply because the force of aerodynamic resistance is acting against the force of gravity, therefore reducing the acceleration of the ball and eventually bringing it to 0, and that's why we have the terminal velocity. A second experiment that is performed is an upward launch experiment. In this case, we start with an initial altitude of 0 meters and launch the ball upwards with an initial speed of 100 meters per second. As previously, the mass of the ball is 200 grams and diameter is 10 centimeters. The plot here shows the velocity-altitude trajectories for the two cases. In blue is the case with aerodynamic resistance, in red is the case without aerodynamic resistance. So the ball starts from this point here, which is an initial velocity of 100 meters per second. It's a positive velocity, therefore the velocity points upwards. So initially the ball will move away from the ground and the initial altitude is 0. So the ball starting from here will then move upwards. The velocity will be decreasing. This is for the case of the of no aerodynamic resistance. The velocity will be decreasing, it will reach 0 and a maximum altitude of just over 500 meters, and then the velocity will reverse direction, become negative, and we will have a symmetric trajectory as for the upward travel, and the ball will reach the ground with a speed of minus 100 meters per second, giving a symmetric trajectory, again due to the reason of the mechanical energy being conserved. For the case of aerodynamic resistance, the situation is very different. Due to the presence of aerodynamic resistance and the dissipation of energy, the ball will reach a much smaller altitude, maximum altitude. This is about 230 meters, and also the trajectory is non-symmetric, again showing the terminal velocity effect when the ball reverses direction after reaching the maximum altitude and traveling towards the ground and reaching the ground with a much smaller velocity, again the terminal velocity approaching minus 28.3 meters per second. This slide presents in more detail the velocity and altitude functions as functions of time for the upward launch experiment. In both cases, we have that for the case of aerodynamic resistance, the ball reaches the ground in much faster time, simply because there is a lot of dissipation of energy during the upward phase, while for the case of no aerodynamic resistance, the ball takes longer to reach the ground. It reaches a higher maximum altitude due to the fact that there is no aerodynamic resistance to dissipate the initial kinetic energy of the ball. We will now present a famous experiment that was conducted in 1586 in the Netherlands, in the town of Delft, by two scientists, Stevin and Groot. This involved an experiment to test a previously held claim that the time that a ball needed to reach the ground was inversely proportional to its mass. So the claim was that a heavier mass would reach the ground much faster than a lighter mass in proportion to the ratio of their masses. So this experiment involved the use of two identical spheres, i.e. the same diameter, whose ratio of masses was 10:1. Both balls were dropped simultaneously from a height of 30 feet. That's approximately 9.2 meters, 9.14 meters. And the time was recorded for the balls to reach the ground. The exact masses were not known, and in this example we use 5 kilo mass for the heavier ball and half a kilo mass for the lighter ball. Also, the diameter is not known, and we use the value of 15 centimeters. So we conduct this experiment. It's a free-fall experiment starting from an initial altitude of 30 feet, and we let the balls drop, and we simulate this with our simulation model. We present on the left the velocity against time trajectories for the two masses. The heavier mass is plotted in blue, the lighter mass is plotted in red. Similarly, the second plot shows the altitude as a function of time for the two masses, the heavier mass plotted in red and the lighter in blue. The simulation shows that the two balls will not reach the ground exactly at the same time. There will be a small time difference of 20 milliseconds for this example. The important point being that in the time when the experiment was conducted, it's very likely that it was impossible to detect a time difference of 20 milliseconds with the measurement instruments of the time. So to the experimenters, it might have appeared that the balls have reached the ground exactly at the same time. Even so, such an experiment was successful in refuting the previously held claim that the heavier mass would reach the ground within a time which was 10 times smaller than the time for the lighter mass. So, in a sense, this experiment was the first experiment to demonstrate the fact that the acceleration of gravity is constant and independent of the mass of an object. A similar experiment was conducted a few years later by Galileo from the Tower of Pisa, or it is alleged that such an experiment took place, and a similar conclusion was deduced. In this slide, we present the question of how would the previous experiment might have changed if we had done it with a higher initial altitude. Remember that the initial altitude used in the Delft Tower was only 30 feet, 9.14 meters. How would the change of time of the two balls reaching the ground, how would that vary if we started the experiment at increasing initial altitudes? So this can be performed using our simulation model very easily, using the same values of masses of 5 kilograms and half kilogram, diameter of both spheres 15 centimeters, and we repeat the simulation experiment for increasing initial altitudes up to just over 900 meters. The initial altitude is plotted here on the x-axis, and the time difference, delta t, which represents the difference in time for the two spheres to reach the ground, is plotted in the y-axis in seconds. The first point here corresponds to the Delft Tower experiment, which was shown in the previous slide that it was only 20 milliseconds. Therefore, very difficult to see in this slide. If this experiment was conducted at the Tower of Pisa from approximately a height, let's say from 50 to 55 meters, again with these values of masses, the change in time between the arrival of the two masses would have been less than half a second. Again, difficult to detect during the late 16th century, and possibly again would have given confidence to the experimenters that the previously held claim was wrong, which it did. If the experiment is conducted, let's say today, or in the late 19th century from the Eiffel Tower, let's say from a height of approximately 280 meters, the time difference of the balls reaching the ground would have been approximately 3 seconds. That is a noticeable time and would have shown that the effect of aerodynamic resistance interferes with the experiment and therefore needs to be taken into consideration before deducing any conclusion regarding the acceleration of gravity. Of course, by this time, in the late 19th century, when the Eiffel Tower was built, it was well known that the acceleration of gravity was constant after the great work of Sir Isaac Newton, who formulated Newton's equations of motion and the law of gravitation. If the experiment would be conducted today from the observatory of the Burj Khalifa Tower, which is the tallest tower currently in the world, with its highest point roughly at 880 meters, if the experiment was conducted from the observatory, which is approximately 560 meters, then two balls would have reached the ground with a time difference of just over 4.2 seconds. Again, a noticeable time and very easy to measure with the time measurement instruments that we have today in our availability. Moving on, what would happen if these experiments were conducted with increasing masses? So the previous two slides consider the two masses being 5 kilograms and 0.5 kilograms. What if we maintain the ratio of 10 to 1, but we increase the value of the masses? So the blue case corresponds to the previous case, where the masses are 5 kilograms and 0.5. The red line corresponds to the cases where the masses are 10 kilograms and 1 kilogram. The green line corresponds to the case where the mass is 15 and 1.5 kilograms. Again, in three cases, we maintain the 10 to 1 ratio, and the diameter of the spheres is always 15 centimeters. Again, we plot the initial altitude at which the experiment is conducted against the time difference in seconds required for the two masses to reach the ground. Well, not required, but recorded. When the two masses reach the ground, there is a small time difference, delta t. So it's obvious to see that for our three hypothetical experiments from the Tower of Pisa, from the Eiffel Tower, and the Burj Khalifa Observatory, using increasing masses would have made the effect of the aerodynamic resistance less noticeable, and therefore the change in time of arrival of the two masses would have reduced considerably. For example, for the Eiffel Tower, whereas with masses of 5 kilograms and 0.5 we had a delta t of over 3 seconds, if the masses increase to 15 kilograms to 1.5, then this delta t comes below 0.5 seconds. So using higher values of masses and smaller altitude would have helped the experiment in reducing the influence of the aerodynamic resistance and therefore verify the true theory that we know today, that the acceleration of gravity is constant for independent of the mass of an object. Going back to the initial differential equation, we can see that from the differential equation that choosing a larger mass, we can see where the mass constant appears would make the effect of the drag force smaller compared to the effect of the gravity force. Remember that this is the expression for the aerodynamic resistance, and using a higher mass makes this term smaller compared to the acceleration of gravity effect. Also, choosing a smaller initial altitude would not allow the effect of the drag force to become significant, since the speed would not have time to increase much. Therefore, this term, the v squared, would not have increased a lot, and therefore would have kept the aerodynamic resistance force smaller, therefore again not disturbing the part of the acceleration of gravity. So we see that both the equation and the simulation model can give a good interpretation into why an experiment would be more successful in removing the influence of the aerodynamic resistance on the gravity force. Finally, to end these online presentations, we can draw these conclusions that simulation software can apply sophisticated numerical algorithms to solve numerically complex and nonlinear differential equations that we would otherwise not be able to solve analytically. And in practice, if we would like to model, physically and mathematically model any real system, at some point we would have to use nonlinear and complex differential equations. So simulation software would be our only way to solve these equations and get some information regarding the dynamic behavior of a physical system. Furthermore, in the second conclusion, we see that these numerical solutions can be very beneficial in providing guidance for the design of better experiments with less effort and in less time. So the simulation model and its numerical solutions could be used as a help and guidance to design better experiments if we wanted to design experiments to actually test the theory experimentally, which is also a very important step in verifying a theoretical hypothesis, as was done at the times of Galileo and many scientists throughout the ages. So I would like to help by supplying these presentations, and I hope you will find them helpful in your studies, and thank you for participating.